And because I need the language of computers to formulate these paradoxes, unfortunately, I need to subject you to at least 10 minutes of theory development. So I've hopefully provided you an entire 4-page document for the things that I want you to have seen before we continue. But let's just talk. So please also go to this link if you don't have a paper copy. It's fairly important that you at least glance at it. So a little bit of the history. So starting in 1888, Dedekind first successfully developed some axioms and then proved using recursion various properties of these types of functions. Okay. So you start with m+1, and then you just recurse and develop things like m+n, and then recurse on that to get m times n, and then recurse on that again to get m times n to the n. Okay. So that was in 1888. 1890s, early 90s, Peano looks at all this and develops his axioms. Okay, so if you just look on Wikipedia, there's 5 axioms, and then an induction schema for induction. I will also mention the Peano axioms later in this talk. And then jump forward 40 years, 1930s. There's a bunch of these mathematicians, Godel, Church, and so on, who are developing this notion of recursion. Okay. And if you look on the document at the first definition, partial recursive function, okay, there are 6 total items. Okay, and the first 5 are what Church, Turing, I mean not Turing, Gödel, and the other people, okay, come up with. Okay, but unfortunately, that was incomplete. Okay, so their goal was to try to get this formalism to hold all this mathematics that had been developed. Okay, all of the definitions that people have set forward, they want to formalize in just a couple axioms. For example, primitive recursion, if you look on the sheet. Unfortunately, it was incomplete. Okay, so there was an example of a function in 1928, so even before these guys had started working on it, from Ackermann. You might have heard of the Ackermann function, and this is the Ackermann function that grows really, really fast, okay, and is beyond primitive recursion. So, okay, too bad. They see this letter, okay, that Ackermann writes them, and then they fix it. Okay. And so we get the 6 items in the definition of partial recursive. Okay, so if you look, there are 3 classes of initial functions. There's the 0 function, which should obviously be a function we know how to do or work with. There's the successor function. There's the coordinate projections. And then there's 3 operations. Composition, which obviously should be computable. Recursion, which obviously should be computable. And this weird minimization thingy. Okay, this is the missing one that eluded these smart people for a couple of years. So that's the history. Ultimately, they ended on this class of functions called partial recursive functions. But people were still unhappy because people kept coming up with new ideas, and they were like, how are you so sure that your 6 axioms capture the entirety of all the functions that we care about? That's a pretty, grandiose claim. 6 things, and you captured all of mathematics. Are you serious? But in 1936, okay, Turing comes along and finally provides, philosophical justification for the correctness of this definition. So that's Exhibit B. Okay. I should mention that in this first half of the talk, I want to prove a case to you. And my case is the following slogan. Okay, so everybody knows, especially now that we're in the 21st centuries, computers can do arithmetic. Okay, this is a no-brainer. We all know that computers can do arithmetic. But more profoundly, the opposite is also true. Arithmetic can compute. And the goal of the first half, or not half, first chunk of this talk is to convince you that this is true. So what did Turing do? Okay, so Turing comes along and tries to formalize what it means to be an algorithm, okay, to do an algorithm. Okay, so please look at Exhibit B. Here is his sort of explanation. Okay, so he says that this deterministic Turing machine, okay, this you should think of as an idealized agent executing a deterministic algorithm. Okay. And so it is idealized in the sense that there is an unlimited supply of time and scratch paper, but it is still like a human understandable algorithm in the sense that this agent only has a finite or bounded amount of memory, okay, in his head. Okay. In other words, he can only think finitely many thoughts. Okay, I think that's a reasonable assumption. There are finitely many possible symbols to write in each cell. Okay, that's also reasonable. I've yet to meet somebody who can write infinitely many things on a piece of paper. And also the ability to know or remember the path to only finitely many neighbors of the paper he's looking at. Okay, this is also reasonable. It's not reasonable to expect somebody to be able to jump forward like a billion papers into, you know, the next universe just to read a certain piece of data on it. Okay, he has to walk step by step if he wants to get there. So that is the definition of Turing machine intuitively. That's a lot of talking. So let me show you an example of a Turing machine. Okay, I've written the definition for you, the whole thing, you know, there. You can look at it, but it's actually, you know, I think if you see an example, then I don't have to go through the definition. Okay. So the idea of a Turing machine is that you have a bunch of states. Okay, these are the mental states of which there are finitely many. There's Q0, which is the initial state, the one you start at, and then there's Q halt, which is the halting state. Okay, if you reach the halting state, then you're done with your computation, and then whatever you have on your tape, okay, is gonna be the end of your computation. Okay, so let me roughly set the stage. Okay, so the Turing model of computation, I told you that there's, you know, all this finite, you know, unlimited supply of paper, but I can only look at one piece of paper at a time and so on. You can do various reductions, and I spelled them out a little bit in Exhibit B, that you can always reduce it to just symbols consisting of 0, 1, and space, okay, like I have here, and one tape, and one head of attention. Okay, so here is me, okay, and here's my paper on which I can only write one symbol. Just for an example, how do you convert, you know, multiple symbols? Suppose you have a much larger symbol set. How do you reduce it down to just 0, 1, and space? Well, you just group multiple blocks of these symbols as one super block. Okay, and that way you can encode, you know, more symbols. But ultimately, as I spell out, you can reduce down to this super simplistic setting in which you have only 3 symbols, 1 tape, and in fact, you can even get rid of this space. Okay, you can even do that. Of course, you can't get rid of 2 of them because otherwise there's nothing to say. Okay, so there are mental states, okay, and there's a tape, an infinite tape indexed by integers, and we're in a certain position, which is called the current position. So I'm going to give you an example of the addition. This is 1. This is the Turing machine to add 1. So I'm going to have 3 states. Q is equal to Q0, which is the initial state, the starting state. Q1 is carry 1 to the left. Okay, and Q2 is the halt state. Okay. And I'll have a transition function. So what does this transition function do? It takes in a mental state. Okay, I'm in a certain mental state when I'm, you know, performing this computation on a given, you know, clock step. Okay, and it is given a certain thing that I'm reading. So for example, if I read the number 1 and I'm in mental state Q0, which is the start state, then what do I want to do? I'm going to keep it at 0, and then keep my mental state in Q0, and then move to the right by 1 unit. So the transition function takes in what I'm reading, my current mental state, and outputs what I'm going to overwrite in that space, the next mental state I'm in, and then the direction I'm walking. So one run of this, okay, I'll write it here. Maybe I should have given you the intuitive description of the algorithm first. So Q0 starts here, And what it does, it just keeps hopping to the right until it hits space. Okay. And then once it's reached space, then it adds 1 starting to this number. Okay. So here, if I read 0 or 1, then I should continue moving to the right and not change my mental state. Okay. So let's get to this plot. Let's suppose I'm in, the starting state and I read a space. That means that I'm here, right? And that means I should start adding the 1. So Q, the result of this should be keep the space there. Okay, I'm not gonna write something here, but my mental state should be changed now Q1. And then the next step I take is left. Okay, so when I'm here, this guy goes da 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 da. Okay, and then my mental state changes to Q1. That's I'm starting to carry 1 to the left stage. And then I'm going to move 1 left. And then T of 0, 1. If I'm in Q1, okay, and I read a 0, then what do? I replace that with a 1, right? And then I'm in Q2. Okay, Q2 means there's nothing more to do. Okay, because once there's a 0 and I add a 1, that's the end of the adding 1. And then this is moving left. Okay. But if I see a 1 and a Q1, okay, then I first have to change that to a 0, right? And then I have to continue to be in Q1 state because I need to carry the one more step to the left. So this is roughly what a Turing machine looks like. Okay. And you can see the run of the Turing machine in Exhibit B. Okay, I wrote out the pictures for the run. Yes?
Do you fill out the left with zeros or spaces?
Spaces.
Spaces. So shouldn't we also have a chance that it's space? Like if I had 1, 1, 1, 1.
Well,
and
this is the Turing machine that adds 1 to the number that I'm at. Okay.
But what if the number you're at is 7? So it's 1, 1, 1. Then I go over 0 to need to carry 1, 0 need to carry 1, 0 need to carry 1, and now I'm carrying 1, but I'm
yeah. I haven't finished writing it.
Oh, sorry.
Yeah, you are entirely correct. If I have a space here and Q1, then you should fill it into 1 and then halt, and then continue moving left. Okay, sorry. Yes, so you can imagine that just doing this for more complicated things, you can figure this general model of computation. Let's see. Okay, so let's keep trying. Okay, so my goal right now is to convince you that computers can do arithmetic can compute. Okay, so my first step is to convert all of this into an arithmetic formula. Okay, and I'll do this very sketchily. Okay, so given first, let me define a function pair from n cross n to n. Okay, which you can think of as mapping each pair bijectively to n. Okay, and this is the Cantor bijection. So we have this string of integers, and then Cantor famously, figured out that if we do this, then that bijectively maps n to n squared. Okay, and the inverse of this map is this pair function. Okay, and there's a formula on the sheet. Okay, amazingly, it's a polynomial. So given a configuration C, which consists of my current mental state, Pj, okay, the tape P, and then the position that I'm at, okay, which I'm going to denote by this arrow. I'm going to code that by pair J, pair, okay, LC. I'll discuss this in a minute, and so forth. Okay, where LC is reading. Okay. One more remark. I said that we could remove the space. Okay, and so it is now at this step where I'm going to ask us to remove the space to even simplify it one step further. Okay, LC is the result of reading everything up till the last one, as a binary number. Okay, so for example, if I have you know 0, 1, 1, 0, 1, 0, 1, okay, then L of C would be starting here, B to the left, and I get the integer 5. I think that's correct. Yes? Anybody? And then R of C is reading from here, but backwards. Okay. It's a little weird. Okay. Again, I'm going through it a little fast, but just to give you a rough flavor. So the state of this configuration, okay, sorry. The code little c of this configuration is this. Okay. So I have these 3 pieces of data that will all bring me back to these 3 things. Okay. J will tell me what QJ is. And the fact that I know L of C and R of C tells me exactly what numbers are on the left and what numbers are on the right. Okay, you can imagine however I can define L and C that they're somehow encoding what's on the left and what's on the right. Okay. Then the state of C is just the first element of this code C. And then the left of this configuration is the first element of the second element. Okay. So one can harvest out the state and then what's on the left and what's on the right just from this one number. Okay, so C is again an element of N. And now let me give you an example. To encode the transition 0Q1 maps to 1Q2 left, which was over there. Okay, I'm going to do the following. I'm going to define the predicate, valid step, C and C prime. Okay. And what I'm going to do is I'm just going to check that C is a valid configuration. Okay, C prime is a valid configuration. The state of C is equal to 1. The state of C prime is equal to 2. And also that everything else here is coded correctly. For instance, if I'm currently at 0, right? Then left is going to be this number in binary, okay, whatever that number is. So if I move 1 step to the left, what's the new left number? That's just this number divided by 2, right? So I want, for instance, left of C prime to equal left of C divided by 2. In other words, I move the 2 on the other side. So this is one way to verify that, you know, this did exactly what I thought it would. Any questions about this bit? Okay. And similarly, right of C prime, if I move here and I replace this with a 1, that's the result of multiplying this number by 2 and then adding 1. Okay, because again, I'm reading that way when I read this this right number. Okay, so very roughly speaking, I can encode every transition as a long series of steps. Okay, and I give you an example in exhibit C. Okay, so it's just like 7 different things added together. Okay. Are people somewhat convinced that I can encode the execution of a Turing machine into just pure arithmetic statements about natural numbers? Okay. One more thing. Okay, last exhibit, exhibit D, okay, is where I'm going to talk about connections to arithmetical truth. Okay. So, the previous result tells us that if I have a Turing machine, then I can associate with that some partial recursive function. Okay, given by all this, you know, nonsense. Okay. And now my goal is to sort of give you an idea of, just to keep going further, to get to a statement about, a proof statement about numbers. What can I say? Okay. Yeah, I don't want to get into this. If you're interested in the details, please look at the links provided. What I want you to point your attention to is just the fact that just show you what the statement is. Oh, damn. I think I'll have to ask somebody to put that back up for me. So the key point is the following. I converted all the Turing machines to partial recursive functions. Okay. And now partial recursive functions can be understood as just formulas in arithmetic. Okay. And this is roughly how you do it. Okay. So let me show you, for example, this primitive recursion. Okay. Here, you may think, how can I transform this, function, and the fact that, f at these values equals to some output y, okay, into a statement about arithmetical truth, using the very limited language of logic that we have. Okay, I listed for you the symbols of logic, okay, in Exhibit D. They're just parentheses, exist symbols, equality symbols, 0 plus less than. Okay, so how on earth do we encode all of this, recursion, complexity into just those few symbols? Well, you do it step by step, and then you get, these formulas. Okay, I'm not going to go into it in depth, but hopefully you believe me that somebody has written out the formulas, and you can just accept that they're long but not too long. Okay, let's see. So that is the first chunk, to hopefully convince you that computation is ultimately just statements about natural numbers. Okay, and if I could and we'll get into it more, but hopefully now that I convinced you that there's a very, very tight relationship between arithmetic things and computational things. And everything that computers can do, arithmetic can do as well. All right, okay. Time for the paradoxes to begin, finally. The first paradox is the Barber Paradox. Hopefully all of us have heard of the Barber Paradox. It's the statement that the following sentence doesn't make any sense. Okay. So let's suppose that there's a barber B, okay, who shaves all and only those people who do not shave themselves. Okay. And of course, the paradox is this doesn't make any sense because does B shave himself? Okay. Please nod if you've seen this paradox. And okay, good. Now let's go to Turing machine land. Okay. And I'm going to rewrite this paradox in Turing machine land. I'm going to define a program or a Turing machine. Okay, it doesn't matter. Just something along these lines, which does steps algorithmically one by one. Okay. Whose name is Contrarian. Okay. And what Contrarian is going to do is that it's going to take in some string s. Okay. Tries to interpret S as the code, of a valid one input Turing machine. Okay. It returns like abort, stop, if it cannot interpret it as a valid one input Turing machine. Determines if P of S, which is the program that is encoded by the string S, okay, if this program halts or runs forever, okay, on the string S, okay, and then do precisely the opposite. So in other words, concurrent takes in string S. If it's the code of some program, I'm going to analyze this code, determine if that program will halt or run forever. And then if I determine that that program halts, then I'm going to run forever. Okay, I'm just going to do while true, right? And if I determine that P of S halts, P of S runs forever, then I'm just going to be like, okay, stop. Okay, so that is contrarian of S. Okay. It reasons the string S and does precisely the opposite. It's a very contrarian behavior. In other words, the contrarian program satisfies contrarian halts on all and only those programs. Okay. Or all and only those source codes of the programs who do not halt on their own source code. So hopefully you see that these two paradoxes are isomorphic. Okay. So what is the takeaway? Okay. The takeaway of the Barber paradox is that the Barber cannot exist. Okay. The takeaway of this paradox is that the concurrent cannot exist. Okay, fair enough. So now what? First of all, let me point out why can't this concurrent exist? At what step of this, pseudocode is do we run into some problems? What big issue am I brushing under the rug?
You need to solve determine if PS halts or not.
Exactly. Okay. So I need to be able to look at the source code of a program and determine if it halts. Okay. And so this program does not exist because I would need to know the halting problem to solve it. I'll get back to this. Okay. But for now, please, bear witness to the fact that the halting problem is showing its face. Okay. Normally, we don't go around quizzing each other on well, I'll just leave it at that. So, as my title suggested, paradoxes are interesting because they seem almost logical, right? It's just almost logical, but not quite. Okay. So here I'm going to make this logical, okay, and then it becomes almost paradoxical, okay, almost false. I'm going to define the computable. And this computable term definitely exists. Okay, it's computable. And it's going to do the following. It's going to take an S, which is the source code of the one input program. Okay, I'm going to do all this checking to make sure that it's valid and whatever. And I'm going to run lexicographically. Okay, so run lexicographically through strings X. Okay, so the first string is 0, the next string is 1, then 1, 0, and then so on. Then, if X is a piano arithmetic proof that P sub S on that source code S, which is, remember what I was focused on over there, if that runs forever, which I'm going to denote with this upward symbol, ascends towards infinity, then I halt. Okay. And if not, if X is a proof, a piano arithmetic proof that PSS halts, then I run forever. Okay. So this is computable now. Okay. I'm just running through strings. And then I'm checking, line by line, is this approved? Does this follow from modus ponens from this, right? All that line by line stuff. And then that's definitely computable. Okay. Then I do this. So this is a computable version of this. Any questions about Mr. Computable Contrarian? Okay. And now I'm going to consider the following. Exactly the same, sort of bad case as the Barber Paradox, right? The Barber Paradox, the bad case was, what does B do on itself? Yeah, yes, please.
Plug in something that's not approved.
Then it just keeps running, right? So if it's not approved, then it just keeps going to the next stream. Yeah. So else it keep looping. So it only does something interesting if it determines that it's approved, which it can do after a computation. Any other questions about Mr. Computable Contrarian?
Is the proof finite that we're reading?
Yes. Well, it's I start with the axioms of piano arithmetic, which are in Exhibit D. Okay, you can read them. And if I start with the axiom, and then the last statement is P of S runs forever, then that's a proof, right? Win. Okay. So Barber, the bad case was Barber, what does it do on its own? So now I'm going to plug in its own source code as S, okay, which I can do, right? It's a program, it has code, I can plug it in. Okay, so I'm going to define this sentence B for Barber of computable contrarian evaluated on the source code of computable contrarian. Okay, and these little bracket symbols mean source code of. Then, a program either halts or doesn't, right? There's no in between. You run the little creature and it does its thing, and it either halts or doesn't. So either it halts, okay, or runs forever. Okay, so one of them is true and one of them is false. Okay, which one is true? If B truly halts, then the only way it can have halted is if it entered the first branch, right? In other words, it saw a paid proof that PS of S, which is itself. Okay, maybe I should slow down. What happens when I plug in its own string into itself? Then if we just look over here, PS is the program with that source code. In other words, computable contrarian. S is the source code of computable contrarian. And so B satisfies B. Let's graphically run through strings S. Let's run through X. If X proves, which is this little funny T symbol, if X proves B runs forever, then I halt. And if X proves that B halts, then I run forever. Okay, so B satisfies that. Right? If you just plug in S is equal to that into this code, you get that. So if B halts, then it must have entered into this branch. Okay. In other words, it must have found a PA proof that B runs forever. Okay. And unfortunately, that's no good. Okay. So assuming PA is consistent, then it cannot be that piano arithmetic proves that it runs forever, but it actually halts. So, this is no good. Okay. So the truth must be that B runs forever. Okay. Sure. But can we prove this truth? Can we prove this truth? So let R for Rosser, okay, this is the good old Rosser sentence, be the fact that B runs forever. Okay. And now I'm going to show you that it cannot be proved. Okay, so this is provable. So I gave you an example of a true but unprovable sentence, and this is very explicit. Okay, you could write this in Python. Okay, so that would give you an example, a very explicit, concrete example of a statement that is true but not provable. How do I write what is a sentence? B runs forever. B runs forever means that for all steps, I never enter the halt state, right? But entering the halt state is an arithmetical statement by all this nonsense that I did before, right? You just look at the transition functions and you show that we never enter the halt state, and so that is an arithmetical sentence, right? That's why I had to do all that nonsense before. So now I will show you that this is unprovable. Any questions before I do that? Yes, please, Matt. Yes,
Just to clarify,
yes.
so you're saying that B runs forever is unprovable from the
From piano acts,
Okay,
yes,
because
that's right.
obviously we just proved it.
Yes, but we proved it assuming PA was consistent. So this is a piano arithmetic proof that if PA is consistent, then B runs forever.
Gotcha.
Okay, so this will
Gotcha.
very shortly prove Gödel's second incompleteness theorem.
Fair enough.
We'll get to it.
So you're talking about plugging in a code, is its code a proof that it run,
No, its code is just this thing that I erased.
yeah, but so then how does, it seems to me like if I plugged in the contrarian as the contrarian, it would just be like, that's not a proof, that's a program.
It makes more sense if you look back at this thing that I erased.
The program that runs a program and tests whether it
Okay, so
has.
If it helps, imagine computable contrarian as a person who is actually reading code. Okay,
It's reading code to determine.
And I just happen to be reading the algorithm that I'm running to determine to do my own thing. It's very trippy, but it's still logical. Okay, that's the important part. Okay. Suppose that negation of R, or in other words, B halts, is provable. Okay. Then there exists a shortest proof. D. Okay. Of the fact that B is going to halt. Okay. And so in other words, I'm going to go into the branch. I'm going to go into the second branch. So go into second branch. Unless, of course, I already entered the first branch. Okay, so if there is a shorter proof, if there is this proof P, okay, then this step will find it, okay, because it looks for these strings. But the only way that I would have made it here is if I didn't already halt by going into branch 1. Okay, so this is pretty important. So unless already entered first branch. Okay, but can I have entered the first branch? Is it possible for me to have entered the first branch? In other words, is it possible that there exists a Q which comes before it lexicographically, Q less than P, that proves B up? Is that possible? Well, in this case, then it would have entered the first branch, right? That's what I just said. And in which case, B will have halted, right? Like B would have actually halted. But if B halts, then that is something that, can be finitely witnessed, right? If B halts means the condition to enter, that first branch was met, and that's something that has a finite witness. In other words, that's just a number that piano arithmetic can see. So in other words, if B actually halts, then PA can prove that B actually halts. Okay. But then this is a problem because now PA is proving that B halts and also B doesn't halt. Okay, so this breaks the assumption that PA is consistent. So assuming that PA is consistent, then this cannot have happened. So let's just say bye-bye. This cannot have happened. So now I'm firmly in the second branch. Okay. Which means that the conclusion is that B must, in fact, run forever. Sure. But then what? Then piano arithmetic can go through string less than P, or just say less than P. Okay. See that they are not proofs of the statement R. Okay. And then recognize that P is a proof of negation of R. Okay, which was by definition what P was. And hence, in second branch, what I should say is PA can go through these strings, see that they're not proofs, recognize that P is a proof, and therefore that is itself a proof that B halts. Right. So this in itself is a proof in piano arithmetic that B halts. Okay. Oh, sorry. I jumped the gun. Please hold. And hence enter in the second branch and conclude that B runs forever. Okay. This can be formalized into a piano arithmetic proof that B runs forever, because that's the conclusion of this big block. Right. So again, I have that piano arithmetic has proven that B runs forever, and also that B halts. Okay, so again, I reach contradiction. Okay, sort of long-winded. Okay, you can also do the same thing for suppose that R is proven, and it's all the same. So what's the takeaway? The takeaway, first of all, is that I've given you an explicit example of a true but unprovable statement. But also, let's understand this function R a little better. I'll write it here. So R, which is this statement, B runs forever, okay, is true but unprovable, and formalizes the following paradox, which is called the Godel paradox. For every proof of me, okay, exists a shorter proof of my negation. If you walk through the logic of the statement R, okay, which let me just do. What is R? Hold on. Somewhere. So lost my notation. Oh, well, let's try to reason through this. Okay. For every proof of me, there exists a shorter proof of me. So what is the statement R? The statement R is the statement so that R is true, which means V runs forever. If and only if. For every proof of me, which is this here, right? I must have come across this before that one, right? Because that's the only way that I would have ended up in this conclusion. The only way for B to have actually halted is if it went into this branch before it went into this branch. Any guesses? So R is true, implies that for every chance I had to enter in the second branch, implies that for every chance I had to enter into the first branch, I must have entered into the second branch before that, which is this statement. For every proof of me, there exists a shorter proof of my negation. Okay. So R is true if and only if the Rosser sentence of R is true. And this is very closely related to the famous liar paradox, because if we just interpret this statement, that means that R says, okay, I'm going to use the word loosely, R says that I'm improvable. Right. Because if for every proof of me, there exists a shorter proof of my negation, there cannot exist any proofs of me, if the statement is actually true. So R, you can think of R as being very closely related to the liar paradox. It's the third paradox of evening, which is this statement is false. And of course, this paradox is paradoxical, but how do we make it non-paradoxical? Well, it's just replace false with unprovable. The statement is unprovable is exactly what this R seems to be asserting. Okay. So we've seen the Barber paradox, okay, and we strengthened that. Oh, sorry, we like tinkered around with it to get to the contrarian, which also doesn't exist. And then we went from the contrarian to the computable contrarian, and then we were able to derive a bunch of interesting theorems of logic from that, including the first and second of the incompleteness theorems. The first statement says that assume a formal system S is consistent and is powerful enough to reason about arithmetic. In other words, powerful enough to reason about the halting of machines, okay, which I already told you is a statement of arithmetic, and is strong enough for arithmetic. Okay. There's one more. I'll add it later. Assume that it is consistent, strong enough, then there exists true but unprovable statements. Okay. And the second statement is that S cannot prove its own consistency. Because if it could prove its own consistency, then it could indeed prove that, you know, by this argument that I had done previously, it would be able to prove it, which I just argued was not possible. So I have proven both the Gödel incompleteness theorems using computable contrarian. Okay, that's pretty good track record. I don't think I have too much time for more, but I want to emphasize the profundity of this result. Okay, this is, I think, very, very strange. So I'm going to go back to the halting problem, which I had told you was the key to this contrarian being not possible in the real world. So let me return to the halting problem for my, I think, maybe marks. So I told you that halt is not computable. That falls right out from looking at this program contrarian and looking at where possibly could difficulties arise. So now let me give you this definition. The definition of the Busy Beaver numbers. BB stands for Busy Beaver. This is the longest runtime. Sorry, not set. Longest runtime of Turing machine of length. That's the name of halting Turing machines of length less than n, where length is some notion of length for the data of the Turing machine, right? You can define length however you want. I don't care.
Both related to the number of states and the number of.
Yeah. So somehow you would encode your Turing machine as some data, right? That is going to take some amount of bits, and that's going to be the length. Whatever. So the Busy Beaver is, for example, Busy Beaver 5, which was very recently just computed, actually, a couple months ago, is look at all 5, length 5 Turing machines, okay, and some of them will halt, some of them will not halt, and just take the maximum of the runtime of those who halt, right? That's a finite number, right? It exists, right? But the fact that we cannot compute halt is the same thing as proving that we cannot know these Busy Beaver numbers. Because if we knew the Busy Beaver numbers, we could just run the Turing machine with a given number, given length, that number of steps. And if it hadn't halted by then we must be able to conclude that it runs forever. Okay. So if I know halt, if I know halt, then I know the entire set BB of n, and vice versa as well. If I know BBN, then of course I can figure out halt. Okay. We say that these are Turing equivalent. If I can use one as an oracle to figure out the other one. So these are like actual numbers, okay? Like they're not abstract entities, they are actual numbers, and we can never know them. Okay. In fact, we cannot even prove an upper bound for them. Because suppose f was a computable, sorry, suppose that I have a computable function, computable, f, such that BB of n is less than f of n. Okay. Then I can find an algorithm to determine if it halts, right? I can just run the program f of n many steps, and then if I haven't halted by then I can conclude it runs forever. So in fact, there is no computable upper bound for the Busy Beaver numbers. Okay, they are so far beyond human comprehension. I labeled this section in my notes the monstrosity of truth. Okay, so like these cosmic horror, fiction, right? These are literally unknowable, right? You can, provably unknowable. Okay, but I will scare you even more. Okay, so let me. So um, I told you that at the very beginning that well, okay, maybe I'll just argue it as follows. My claim is as follows. So right now I have BVN is Turing equivalent to the machines or the strings S, such that, let's say, the program with that code S halts on its own input, just so we can work with a set of numbers. And I'm going to say that this is also Turing equivalent to all true sentences that begin with one or some block of as extension quantifiers, and then one arithmetic formula with only bounding quantifiers. This bounding quantifiers bit was the part that I skipped over at the very beginning. You can look at the handout for details. But the point is, if I okay, so first let me show you that if I knew the halting, if I knew halt, then I could know in the entire set of these are called sigma 1 truths. Okay, I will know all true sigma 1 statements. Okay, why is this true? Bounded quantifiers are things that I can just compute, right? These are bounded quantifiers are like exists y less than some bound 100, or for all y less than 100, right? These are the quantifiers that are in this statement. Okay? These are all things that I can compute. And exists, well, that's just there exists one input, say, so that this is a certain value. Okay. Well, I can just define the machine which just searches through the space of inputs, okay, and tests this thing. And if it's true, then it will halt, right? So I can define the machine and sub phi that loops through inputs, computes 5x or psi of x, okay, and then if true, then I halt. And if it's not true, then I run forever, right? So the halting of this machine completely determines whether or not this is true or not. So if I knew the halting set, okay, or if I knew the Busy Beaver numbers, then I could determine arithmetical truth. And the same is backwards. The same is true the other way around too. Because if I could prove this, if I could know all of these statements, then Turing machine's halting is going to be one of these statements, right? There exists some input such that I reach the halting state. So that all sigma 1 true sentences, that's equivalent in computability power to the Busy Beaver numbers, or in other words, the halting set. But of course, there's a lot more formulas than just sigma 1, right? So even just one alternative exists for all. These are called I2 statements. Okay. That is beyond this reach. Okay, so Busy Beaver numbers themselves already, unfathomably beyond human reach. Okay. But Busy Beaver numbers, their power is only, for these sigma 1 sentences. But there's an entire tower. This is one quantifier. And of course, there's an entire tower. This is arithmetic truth. And knowing the Busy Beaver numbers, which already are, an eldritch horror, okay, is just this little much. So truly, this is the monstrosity of truth. Okay. I think I'm out of time. If there are any questions, please ask. Yes, Sam?
So you mentioned that we can't know all of the Busy Beaver numbers,
Yes.
but some of them have been computed. Do we
Yes.
know how big n has to be before we can't?
Yeah, so a very easy bound is you just look at the Turing machine, which runs through proofs like piano arithmetic proofs. And so, for example, the machine M, which Lex runs through strings S, and if S is a piano arithmetic proof that PA is consistent, okay, then this we cannot know the halting of this, right? Assuming that PA is consistent. Okay, it was like forever beyond the reach of proof. Okay, or if you think PA is too weak, you can change it to ZFC, whatever. Like any axiom set you want, okay, any complexity you want, you can just make this machine, right? And there's a pretty short list of axioms, and the code that will run this is not too long. Okay, so just naively writing this code, you can prove that Busy Beaver of 10,000 is forever beyond the reach of humankind. Okay, like ZFC cannot decide this number. Okay. And then piano arithmetic is even smaller. So I think people like Scott Aronson, if you just look online, Busy Beaver, Scott Aronson has this wonderful blog post about all these things. And he and his grad student or something managed to golf this down to like Busy Beaver of 700. And so I think now, like the Riemann hypothesis is, all these statements to search through proofs, okay, just this very basic proof searching, machine. You can get, bounds on, famous mathematical problems. Like if you know Busy Beaver of 100, then you will have solved the Riemann hypothesis just by running the proof and seeing if it was there, right? If it's not there, then too bad, right? But if it is there, then you found the proof. Great, win your prize. Yeah. I think Scott Anderson conjectures that like Busy Beaver of 20 is already, forever beyond our reach. Yeah.
What's Busy Beaver 5?
Google it. I don't know it.
What? 4098.
No.
No, I think so. Oh, wait,
No.
47 million. 47 million. Oh, 176.
No, 47 million. That sounds more right.
Yeah.
I also wanted to talk about there's this thing called Kolmogorov complexity, which gives even more natural statements or like simple statements of true but unprovable things. Unfortunately, I didn't get time to talk about it, but if you want, you could just read the Wikipedia page. It's already a good resource. Any other questions about the monstrosity of truth and these cute little paradoxes? Okay.
Thanks, Daniel.